What is the definition in general of a structural isomer? Exactly. So structural isomer, same molecular formula, but a different structure. So that's structural isomer. So it is the structure that is different. And that's how you need to look out for these ones. If you're looking for a chain isomer, it means the chain is the thing that needs to be different. And if you look out for those type of things, then it becomes a little bit easier. The positional isomer means that the functional group must be in a different, and it must be the functional group, must be in a different position. So again, it's the position that's different. Here, it's the chain that's different. And for the last one, it is actually the functional group that must be different. And because of what I've just said about the IEB making it a little bit easy for us, that functional group one is actually the easiest one because there's only one functional group question that they, isomer question that they can ask you because they have to have the same molecular formula, but they have to have a different functional group. And for all these others, the alkenes, the alkanes, there's nothing that we do in the IEB. There could have been if we did aldehydes, because then there could have been alcohols and aldehydes. But because they took all of that out, the only functional group isomer that you can get is one with two O's. So you're going to see a COOH. So only one is where there are two carbons. So if I draw two oxygens. So when you're drawing a molecule, remember for an ester, we have the O somewhere in the middle, and then the carbons carry on. Let's check if you can name this one for me. Let me put the double O there. Okay, so now if the double O is there, what would the name be of this molecule? Perfect, well done. Okay, so now if you're looking at this molecular formula, we've got 1, 2, 3, 4, 5 carbons, so it's C5. We've got 10 hydrogens, so we put the hydrogens there, and then we've got two oxygens. So that would be the molecular formula. Now I need something else. So this we know that that's then going to be a ester, and you could just gave me the name. Now what's the only other thing that we do in IEB that has two oxygens in it? Exactly. And that is why I say this one is the easiest because the only thing you need to worry about for your carboxylic acid that you're going to form is that it needs to have the same amount of carbons. So if they just ask you for the name, your life becomes insanely easy because all you're going to think, okay, I need 5 carbons. What is 5 carbons in organic? So you know it's going to be pent, and you know it's going to be a carboxylic acid, and we only work with single bonded carboxylic acid. So you know it's AN, pentanoic acid. Because we only work with terminal carboxylic acid, so we're going to have 1, 2, 3, 4, 5. We're going to have our O, and we're going to have our OH, and the rest is going to be my hydrogens. If they ask you for the structural formula, then that's what you must draw. But just go and check to make sure for yourself that we have the same number of carbons. So let's count. There's 1, 2, 3, 4, 5 carbons. Let's count our hydrogens. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Did I count wrong for the other one? Did I just write it wrong? When did I write H5? I was being blonde, right? Let's go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yes, so I was just being blunt. So that's 10, and that's 10. And how many oxygens do we have? Yeah. So can you see the molecular formula is the same? So we're happy that it is an isomer because they have the same molecular formula. And we're also happy that they belong to a different homologous series because they have a different functional group. Oh, just remember, I didn't actually say that. Just remember that when they have a different functional group, it also means that they would belong to a different homologous series. And the problem is with alkenes, alkanes, alcohols, you can never ever get them to have the same molecular formula and have a different structural formula for those. And so that's why it's always going to be a carboxylic acid and an ester for your functional group isomers. So what is nice about that is if I give you now a carboxylic acid, let's just make it an easy one. Let's say this is our carboxylic acid. Now tell me what could be a functional group isomer of this. Oh, sorry, first tell me the name of this thing. I'm going to test the names all the time. Awesome. So now as soon as they ask you for a isomer or functional group isomer, you know there's only one choice. And what is that one choice? What does it have to be? It has to be an ester. So now you can decide how you want to split it up, but I gave you quite a short one. So there's not that many options. So what remember for an ester you need to split up the carbon. So you can split it up there and put one O there, or you can split it up there and put one O there. So I can say let's keep my one carbon on the side, then put my O, and then I've got my two carbons left. So I've still got three carbons, three carbons. Then here I can decide. You can decide. You can either put your double O there, or can put your double O there. If I put the double O there, what would this name be? Oh, that's right. Yep. Perfect. Yes, um, methyl ethanoate. Yes, perfect. And can you see now it's still got two oxygens, two oxygens. 1, 2, 3, 4, 5, 6 hydrogens. 1, 2, 3, 4, 5, 6 hydrogens. So they do have the same molecular formula, but they have a different structural formula. So that it could be methyl uh, methyl ethanoate, or now here is where we get with the positional isomer. Can you get a positional isomer for the propanoic acid? Can I move that anywhere else? This functional group here. Remember the functional group for a carboxylic acid is the carbon with the two O's and the H. That's my functional group. Can I move that anywhere else? For us, IEB, I can't. So this cannot have a different position at all. So it can't have a positional isomer at all because the only isomer it can have is a functional group isomer, which would make an ester. But if I look at the ester, remember that for the ester, the functional group is the carbon with the O and the other O that then gets attached to two carbons on the side. So that's my functional group there. Can that be moved? It can. So I could say that, and I'm just going to write the name that you, oh, that's not a good color choice there. So you said that this is methyl ethanoate, which was perfectly right. Now you can, and the easiest way, oh, let me just write it before I give you the shortcut. So now I can move this, erase it. I can move this double O to the carbon that's on the other side of the oxygen, it must still be next to the oxygen. So it can either be on the one of the left-hand side of the oxygen or the one on the right-hand side of the oxygen. So if I remove it from this carbon here, it means I need to move it to this carbon here. Just count 1, 2, 3. Oops, too many lines, which would mean that I need to take one of these away. 1, 2, 3. No, I'm talking nonsense. That one should have been there still. 1, 2, 3, 4, 5. No, it is right. No, it's too many. So I was right by removing one. So I need to remove one of these. Yeah, this looks wrong. But yes, I just want to draw it because it can be methyl, it can be methanoate definitely, but it just looks weird now the way I drew it. So let me just draw it again. If it's an O and then a C and then double O. Yeah, they don't do that, eh? They don't really give it to us. It just looked bad to me when I draw it. But you can get ethyl methanoate definitely. So yes, it can look like this. So remember it's a flexible molecule. So if you are drawing it like that, is that what you're saying? This one, oh no. That cannot be there because the single bonded oxygen, so the oxygen has to have a carbon on both sides, because if it becomes like this, there's one electron here on the oxygen that hasn't been shared, and it will grab a hydrogen. So that means it will form a from somewhere, because it's normally in contact with water. So that means that you will form an alcohol, but that they'll never ever ask at school level ever. So that oxygen, the the oxygen between the carbons have a single bond to the one carbon and a single bond to the other carbon. It has to have two bonds. So that means the oxygen that's on the edge always have to have a double bond if it's on its own. Otherwise, it will have to have a hydrogen with it. Does that make sense? Okay. So when they just ask you for the name for a positional isomer for an ester, all you're going to do is you're moving the position. So the easiest way is to just literally swap these around. So if you have a positional isomer, it just means the position is going to change. So it's going to become ethyl methanoate. It's the easiest one that they can ask you, methanoate, because positional isomer for an ester, just swap them around. If there are more than three carbons, then the options becomes multiple options, because if you have 1, 2, 3, 4 and then an O and then 1, 2, 3, just give me a name for this one, for this ester, please. Yeah, say again. Good. So propyl butanoate. And let's say they now ask you for okay, let's first say they ask you for a functional group isomer. What are you going to say? Absolutely, it has to be a carboxylic acid. And your life becomes easy because all you have to do is count your carbons. If you have a structure, you can count them from the structure. Otherwise, you just go to your name and you know prop is 3, but is 4. So that means your carboxylic acid needs to have 7 carbons. So what will my carboxylic acid be? Absolutely. So that would be, what type of isomers would these two things be of each other? Functional group isomers, yes. Now, if I ask you for a positional isomer of that, of propyl butanoate, what would you say? Yeah, you can move it once, but and that would be the easiest way. So if they just ask you for the name, if I ask you for the name of a positional isomer, what would you say? Yeah. Can you see how easy you make your life when you do that? Becomes almost feels like cheating. But yes, the positional isomer, you just swap them around because that is bad because it's such a long molecule. You can move this anywhere else. So you could actually, as long as you keep your 7 carbons, you can say that I can even do 1, 2, and then put my O, and then put 1, 2, 3, 4, 5. So that would be another one. Then that O could be there, or it can be on that side. So that's actually another 2. Then you can move it, and you can have 1 and 6. So there's all kinds of different options, and that's why I say the easiest one, if you get this in an exam, is to just literally swap those two around. And then it's very easy. For the other positional isomers here, you're just going to look, and they are pretty easy because you're just going to look for the functional group and you see, okay, the functional group has moved position. And it's much easier when it's not a ester. So if it's just, if you have something like this where you have a, let's just call it an OH here. So that's an alcohol. What would the name be of this alcohol? Any idea? You do know. Yeah, so you know it's bute and you know it's AN because there's only single bonds, and so it's butanol. But remember, there's one part. Yeah, you need to tell them where that is. So it's butan 2 all. Now, when you look for a positional isomer, it must still have the same number of carbons, same number of oxygen, same number of everything. But the position must move. So the easiest way to do that is to say, okay, the position was 2. So I'm going to move it. So where am I going to move it? To the left or the right? Okay, so if I move it to the left, okay, I'm going to do that quickly. Then tell me the name. Which side must we count from now? Ah, that's why I said it's a trick question. 1, 2, 3, 4. So what is the name? It's still butan 2-all. So is it an isomer? Do they have a different structure? They really don't. All you did is, I'm going to show you now. So all that happened was what we did is we had it, come now, we had it like that. Can you see? It was the second one from this side. Now we have it like that. So it's the second one from this side. So it's actually the same molecule. You're just looking at it from the different side. Remember, these things are flexible molecules. So it doesn't matter what side so when in doubt, if you actually have an isomer or not, then you go and name it. If it has the same name, it's not an isomer, it's the same molecule. And they put that in as a trick question all the time, especially into multiple choice questions. So be very careful, name it, and ask yourself, does it actually have a different name? So I cannot move it. So what we did was move it to the left. So it was here. If I move it to the left, it's still butan 2 also. Where must I move it? I must move it to the right. So if I take it away from here and it now sits there, what is the name going to become now? Right. Butan 1 all. So the position changed. So it was butan 2 all, and now it's butan 1 all. And what's easy now to spot is the position change. So when you see these numbers are different, but then the rest of the name is still exactly the same, then you know it's the position that changed. So it's a positional isomer because the position changed. Happy? Okay, but just be careful that you don't draw the same molecule. And then the one for the chain isomer, that one is the easiest one to spot, because what's going to happen is, instead of having one chain going on like that, so you're still going to have the same number of carbons, and you're not allowed to put a double bond in. So if it had a double bond, it must still have a double bond, because the number those hydrogens must then disappear. So if I move the double bond from there to there, what type of isomer would it be? If I just move it there, so that this would be this but again, 1, 2, 3, 4, 5. No. So this would be pent. Or why would you say 3? Yeah, please remember, number the closest to where something is happening. So 1, 2, 3, 4, 5, and you always put the number of the in on the. It's the carbon that it follows. So you're gonna the double bond comes after number 1, so that's why it needs to be pent 1 in. Okay. Now, if I move that double bond and it's not there anymore, and I move it and I say, okay, it's now here, what is the name going to be now? Can I still number from the right? I'm setting lots of traps for you today. But that's what happens with organic. Organic is really easy, but it's traps. They set the one trap after the other for you. So it's going to be paint. Yes, because I need to start numbering from this side, 1, 2, 3, and now the double bond follows after the second carbon. So the new name would be bent 2 in, and the only thing that's different is the number. So I know that it is a positional isomer. But now if I want this to be a chain isomer, what I need to do, so these two are going to be positional isomers. Now if I want it to be a chain isomer, I'm just taking my numbers away again. Uh, a chain isomer must have a different chain, because remember the word tells you what must be different. So that means the carbons can't all be in a straight line. There needs to be a branch somewhere. So you need to take some of the carbon. So generally you would take that one carbon away from there, but to be an isomer, it still needs to be a straight line. Oh, not a straight line. It still needs to have 5 carbons. So can I move that one that was here? Can I move it here? Is that now an isomer? A chain isomer. Tell me the name for this. Oh wait, let me just leave it like it was. And tell me the name. The names actually help you a lot. So what would the name? Oh, we've got it already. So that's bent. In. Okay. Now, if I move this carbon and I put it here, what would the name now be? It's still pentene. Nice. So is it even an isomer? It's the same molecule. It's just looking at it again from the other side. So when you want to do a chain isomer, You can't ever move the carbon, that last carbon to the edge, move it to the middle, because if you move it from the one edge to the other edge, you're not changing anything. So we need to actually put it somewhere here in the middle. So you could have put it there. Now what is the name? Is it still pent? Because your main chain is, yeah, that's your main chain. And this is just a hanging on, which you already told me. There's my methyl. So it's not going to be methyl. But what must you tell me? What more must you tell me about the methyl? Good. So you have to say 2-methyl and then perfect. So now if you are looking at the position didn't actually change. The double bond was on 2, so we know it's not a positional isomer because the double bond was on 2, it's still on 2. But for the chain isomer, you need to look at the base name. Here it was methyl but-2-ene, so the base was but, and here it was pent. So the longest chain here had 5 carbons, and the longest chain here had 4 carbons. So what changed? The number of carbons in the main chain. So because the chain changed, it is a chain isomer. Here, the positions changed, so it's a positional isomer, and here, the functional group changed, so it's a functional group isomer.